this video, I want to look at an example of what I think of as fancy u-substitution. Our integrand is simply going to involve more than one layer of composition. So I'd like to look at this particular example. I want to find the antiderivative of x squared times the cosine of x cubed times the log of the sine of x cubed dx. Now, I want to analyze this particular problem in the following way. The first thing that I notice is that I have an x squared there, and I have an x cubed, and I have another x cubed. And the x cubes are inside layers of compositions. We have the cosine of x cubed, and we have the sine of x cubed. Those all tell me that it is reasonable to let u be equal to x cubed, and that means du is then going to be 3x squared dx. And I have the needed x squared, so I can fix the integral up by multiplying it by a fancy name for one, namely 3 over 3. And at this point, what I want to do is I want to collect the things that multiply together to form the du. The top three, the x squared and the dx, all go together to form the du, and that x squared and this x squared are both going to be replaced by u's. So when I do this u substitution, my integral becomes 1/3 times the integral of the cosine of u times the log of the sine of u du. Now what I want to do is I want to look at this integral. And this integral itself has a composition. I have the log of the sine of u. Sine is the inside function. And of course, the derivative of sine is cosine. And that is enough to tell me that I need a second substitution. So I am now going to let v be equal to the sine of u. And dv then is going to be the cosine of u du. So I don't even have to fix this integral up. This cosine and that du go together to form the dv, and when I use this substitution, I can rewrite the integral as 1/3 times the integral of the log of v dv. Now at this point, I want to remember something from the first day of class. I want to recall that on our list of known antiderivatives, the antiderivative of the log turned out to be x times the log of x minus x. And the reason why was that when we found the derivative of x, and let me make my handwriting a little bit more clear, when we found the derivative of x times ln x minus x, that simplified to log of x. And so I happen to know that an antiderivative for log x is x times ln x minus x. And I use that fact to get this integral rewritten as 1/3 times the antiderivative of the log of v is going to be v times ln v minus v. And then I'm going to have to add a 1/3. It's important to note that that 1/3 has to multiply the whole antiderivative. The constant of integration is just added on at the end. Now all I have to do is back substitute. I first of all want to remember that v is equal to the sine of u. So I'm going to replace these v's with the sine of u. And when I do, I am going to get an integral that's going to look like 1/3 times v, which is the sine of u, times ln of v, which is the sine of u, minus v, which is the sine of u. And then, of course, there's the constant of integration. Now, to get the final answer, what I have to do is I have to remember that up here, u is equal to x cubed, and so I'm going to plug that in for all of these u's. And when I do that, my final answer to the problem becomes 1/3 times the sine of x cubed times the log of the sine of x cubed minus the sine of x cubed, and then I add whatever constant I want to. This technique of doing more than one u substitution is something that you commonly see when you've got integrands that look like this, where there is indeed a double layer of composition going on. We have the log of the sine of x cubed, and it's okay to bite off one layer at a time when you're trying to find the antiderivative.